Hi, I'm Ryan Benowitz, and welcome to Part 6 of Machine Learning Essentials for Biomedical Data Science. In this video, we'll take a look at how neural network algorithms work. Here's a quick reminder of the parts making up this video series. In the last video, we covered tree-based machine learning algorithms, including decision trees, and tree ensemble algorithms such as random forests, boosting, and gradient boosting. We'll start again by revisiting this diagram of better-known machine learning algorithms that can be applied or adapted to supervised learning problems where we have labeled data. Again, in this video, we'll be focusing on these two groups of algorithms, neural networks and their slightly more complex variants known as deep learning. To understand how neural networks work, let's first begin with a perceptron. A perceptron is a single-layer neural network, also known as an artificial neuron. Here we have a visualization of perceptron, whose architecture is inspired by biological neurons in the brain. Fundamentally, a perceptron is simply a linear classifier with 4 parts. First, we have the inputs to the perceptron as a single layer. These are basically the different input feature values from our dataset, labeled here as x's 1 through 4. Second, we have weights applied to the respective input features, and a bias term added in this inner layer of the perceptron. Third, we have a net sum of the input values multiplied by their respective weights, and then the aforementioned bias being added to this summation. And fourth, we have an activation function. We can think of this as being the building block of the model itself. The activation function serves to transform the input value into some final output value or prediction. So for example here, if our input x is greater than or equal to 0, our output is 1. Otherwise, it's 0. There are a number of activation functions that can be employed, and here I've placed stars next to 2 particularly popular activation functions used in neural networks and deep learning, specifically a rectified linear unit and soft plus. Now that we have the parts of a perceptron and have an understanding of how input feature values ultimately get transformed into an output prediction, let's consider how to train a perceptron from data. First, we want to pick an activation function to use. The activation function is a key neural network hyperparameter. Then we want to optimize the weights and bias in our perceptron with the goal of minimizing our loss function. As with gradient boosting, we can optimize these perceptron parameters using some form of gradient descent. So why might we not just set the derivative of our loss function equal to 0 to solve for the weights here? Well, in contrast to solving for a single parameter, as the number of weights and bias parameters gets larger, with a more complex perceptron or network, the equally dimensioned loss function gets much more complex and computationally expensive to solve, where solving the loss function means finding the unique values for all parameters that yields the lowest overall error. So in this figure on the right, we have a loss function when solving for 2 parameters at once on the x and z axes, with the y-axis being our loss function value. Looking at this visualization, you might spot another issue with respect to minimizing our loss function, and that is that there appears to be more than one place in the loss function space where our gradient would be 0. In other words, there are different possible minimums, some being better than others. This leads us to our second problem, being that the loss function can have local minima, as illustrated in this 2D plot, where we're trying to optimize just one parameter. When using gradient descent to find a minima, it's possible for the algorithm to fall into one of these local or suboptimal minima rather than the ideal global minima. However, notably, the sporadic gradient descent path of a stochastic gradient descent algorithm from our last video can actually help the optimization process to jump out of local minima, ideally making it to the global minima. Now let's build upon our simple single-layer perceptron and expand it to a more complex multi-layer perceptron. One of the best known and widely used multi-layer perceptron algorithms is the feed-forward neural network. This is a network of multiple perceptrons, also referred to as nodes here, that connect in one direction only. Basically, this just means that no cycles can be formed in the connection of the nodes making up the network. Here we have a simple example of a multi-layer perceptron, again including an input layer of features from our dataset, which are subsequently connected to nodes laid out in downstream hidden layers, ultimately connecting to an output layer where the prediction is made. To build a multilayer perceptron, the user has to choose the following aspects of the network architecture. First, the user needs to specify the number of hidden layers that will comprise the network. Typically, for what we think of as a feed-forward network, users would choose 1 to 3 hidden layers. Next, for each layer, we need to pick the number of nodes or perceptrons that will be included within each. Further, we need to choose the number of output nodes comprising the output layer. This may depend on whether we are doing regression, binary classification, or multi-class classification. Also, as mentioned before, we need to select an activation function to be used for all nodes in the different hidden layers. And we need to choose an activation function for nodes in the output layer, that again may be chosen based on the type of outcome our data includes or the type of learning being conducted. And lastly, we need to select a learning rate for the gradient descent algorithm that will drive the optimization of network parameters. In other words, the weights and biases of the model during training. All of these architectural components can be sought to be optimized with a hyperparameter sweep. For instance, a smart sweep using an evolutionary algorithm, as we mentioned in part 4 of this video series. However, it's worth noting that this can quickly become extremely computationally expensive based on the complexity of our network and the size of our data. Now that the architecture of your network has been specified, we need to train the network as an optimized prediction model. Because of the increased complexity and layer dependencies involved in a multi-layer perceptron versus a simple perceptron, for this we'll be relying on a learning methodology called backpropagation. Backpropagation iteratively re-optimizes weights and biases again and again across the entire network, each time applying gradient descent. Using this iterative approach, the parameters of the model slowly converge on or towards their optimal values for minimizing the loss function of the overall model. So without getting into too much of the math, let me try to give you a better intuition as to how this backpropagation works. To illustrate this, we're going to use as simple of a neural network architecture example as possible. Of note, I've borrowed this specific example from the StatQuest YouTube channel as well. Here we have a single input feature connected with weights W1 and W2 to 2 separate nodes making up a single hidden layer, where we can think of the first node, in blue, as including the added bias parameter B1, and further transformation of the input value with the selected activation function. And the second node, in orange, including the added bias parameter B2, as well as a corresponding activation function. And lastly, we have the output layer with its own bias parameter B3, and weights on the incoming edges of W3 and W4. Like in our previous examples with gradient boosting in our last video, and the training of a perceptron a couple slides back, our goal in backpropagation is to calculate the gradient or the derivative of the loss function in order to optimize one or more parameters, where here our loss function is the sum of the squared residuals, or SSR, which again is just the squared sum of the differences between the observed values from our training data and the predicted values from our model. But now here we are simultaneously trying to optimize all neural network parameters, which here includes all network weights and biases. So again, here that would be 4 weights and 3 biases for a total of 7 parameters to be optimized at once. However, due to having so many parameters with dependencies throughout the network, this optimization can't effectively be completed in just one update of all parameters, but rather we will tweak the values of all parameters over the course of many iterations. The main difference between iterations in gradient boosting and neural networks is that instead of adding a weak model to a strengthening meta model, with neural networks, the model architecture remains the same and we just readjust all parameter values each iteration, converging on a more optimal model each time. The backpropagation learning methodology gets its name by calculating derivatives starting from the back of the network, or the output side. As we'll see in a second, this is because the dependencies between each parameter and the output predictions are simplest there. Note that right now, each of our 7 parameters in this network have no specific values, but that's going to change in a moment. However, before we start updating weights, The first thing we want to do is work out all differential equations that will be needed to iteratively update all parameters every iteration. Conveniently, once we come up with all of these equations, they are repeatedly used each subsequent iteration of the training process. Our first equation is the gradient of the loss function with respect to the backmost parameter, which in this case is the output bias, B3. Here we want the equation to calculate the change in our loss function, SSR, with respect to changes in our B3 parameter. This is the same as change in our loss function with respect to a change in the overall network output prediction, multiplied by the change in the network prediction with respect to the change in the B3 parameter. And this can ultimately be described by this equation, which fundamentally just depends on the sum of the residuals, in other words, the differences between the observed and predicted values. Our next two equations for the two weights coming into the outcome node are similarly simple at this back end of the network, as you can see here. Our first equation is for updating W3, and our second for updating W4. In these final equations, here y1, I and y2, I reference the values emerging from the activation functions of the respective nodes found in the hidden layer of this network. Moving on, now that we're getting to nodes closer to the beginning of our network, our differential equations will start getting more complicated, since there's more going on between these parameters and the ultimate outcome prediction of the network. Here we're calculating the gradient for the two bias parameters in the current hidden layer, B1 and B2. Focusing on the first equation, which is the gradient of the loss function with respect to B1, we're finding the equation to calculate the change of our loss function with respect to changes in our bias 1 parameter. This is the same as the product of the change of the loss function with respect to changes in the network's prediction, multiplied by changes to the network prediction with respect to the value that comes out of this node, which here we call y sub 1, related to the y we saw in this equation above. And this is also multiplied by the change in y1 with respect to the change in x1, where x1 is the value going into this activation function. And the last part of this equation is multiplying it by the change in x sub 1 with respect to the change of our target parameter b sub 1. Working through the math, we'd get the following equation for calculating this differential. Note how this is a bit more complicated than the equations we needed for the above three differentials. And lastly, we work out the differential equations for the weights connecting the input layer to our two hidden layers, in other words, W1 and W2. Of course, if this network had been more complicated, having more features, nodes, and hidden layers, we would have needed to work out many additional differential equations than we've covered in this example. And the larger the number of hidden layers, the more complicated the differential equations for parameters at the front of the network will get. Okay, so now let's assume that we've worked out all the differential equations for the parameters required by our neural network. What are the steps we're going to take to iteratively update these parameter values in order to train our network model? First, we need to initialize our parameters, which thus far have had question marks as placeholders. For the weights of our network, the most common approach is to select random numbers from a normal distribution. And here they are. Recall that our weights are a value that we multiply by the value incoming along a given edge. And to initialize our biases, we typically just initialize them to 0. So now we have an initialized neural network, which technically could be applied as a model right away. However, since our parameters were initialized without any learning, we'd fully expect this to be a poorly performing model at this point. So now it's time to learn from our training data. So our second step is to apply the differential equations we previously worked out to calculate the derivative, or gradient, for each parameter. We can do this simultaneously if our neural network algorithm supports computational parallelization. And our third step is to calculate the step size that will be taken to update each of our individual parameters. This is calculated as the derivative for a given parameter multiplied by our selected learning rate, which, as we learned in our last video, can be essential for converging on an optimal model. And the last step in a training iteration involves actually updating each of our network parameters based on the respective step sizes calculated in step 3. And then we simply repeat steps 2 through 4 until the error of our model reaches 0 or some other stop criteria, such as maximum learning iterations, are reached. Here we have a visualization of optimizing a network over individual iterations, where we update network parameters to reduce the error of model prediction in our search for the global minimum of our loss function. So hopefully at this point, you have at least a better conceptual understanding of how neural networks work. However, if you want to understand the math and concepts behind them in greater detail, I'd highly recommend watching the following 4 videos on StatQuest's YouTube channel. I found this channel to include some of the clearest and most accessible explanations of neural networks, as well as many other machine learning algorithms. At this point, we've covered perceptrons, the simplest of neural networks, as well as feed-forward neural networks, which includes more than just a single layer and thus relies on backpropagation to train effectively. So now we'll move on to the very popular topic of deep learning. The term deep learning refers to the training of a neural network with more than 3 hidden layers. And we can see one example of this below with a network that includes 5 hidden layers in its architecture. And at the most basic level, that's about all it means to be a deep learning algorithm. It's just more parameters, more math, and a larger optimization space. However, it's useful to point out that there are several other major variants on the neural network deep learning concept that we will review over the next couple of slides. Let's start by mentioning other supervised learning variants of deep learning. The first are convolutional neural networks, or CNNs. These networks include multiple layers that process and extract features from data. This has been commonly applied for the effective classification of images. To understand why CNNs are so useful for image classification, think about how we might naively try to apply other basic supervised machine learning algorithms to make predictions on a picture. Here we could take each pixel in the image as a unique feature in our dataset, but in doing so, we would immediately lose information about the context of each pixel's position in the original image. CNNs help the algorithm to hold on to and utilize this spatial context. The second supervised deep learner we'll mention is the recurrent neural network, or RNN. In these networks, connections are allowed to form directed cycles, rather than only going in one direction like a feed-forward neural network. This gives RNNs a sort of memory to better keep track of long-term dependencies. This makes them an option for those interested in modeling time series patterns associated with outcome, such as heart rate or working with EKG data. The third supervised deep learner we'll mention is the Deep Belief Network, or DBN. These involve the training of a stack of what are known as Boltzmann machines. Without getting into the details, this can make them effective in the modeling of image, video, or other motion captured data. And we'll end this video and discussion of deep learning by reviewing some of the major deep learning variants designed for unsupervised learning tasks. The first are autoencoders. With these algorithms, information from input nodes are passed through a network with a smaller number of nodes within middle hidden layers, with the goal of reproducing the critical information in the output nodes. In this illustration, we start with a noisy image and employ autoencoders to denoise the image. Autoencoders are often used to conduct some type of dimensionality reduction and are popular for image processing. A second variant here are generative adversarial networks, or GANs. This is a strategy that pits 2 neural networks in contest with each other to form a zero-sum game. So given a training set, this technique can learn to generate a new dataset that resembles the original training set. Here, one network serves as a generator, creating data that can try to fool the other network. And this other network serves as a discriminator, trying to decide if the data came from the original dataset or not. And the last variant we'll discuss is called a self-organizing map, or SOM, which trains a network with competitive learning rather than error correction learning, as we used for backpropagation. SOMs are another example of deep learning for the dimensionality reduction of data. Thank you for joining me for part 6 of Machine Learning Essentials for Biomedical Data Science. In the next video, we're going to talk about a less well-known family of machine learning algorithms called rule-based machine learning. Again, feel free to skip ahead to part 8 if, for now, you prefer to stick with more mainstream machine learning methods. However, rule-based machine learning will likely be of interest to viewers that have a particular interest in machine learning models that are both interpretable and can learn complex multivariate associations in data. If you enjoyed this video, please like and subscribe to follow my future content.